So I guess I'll start by saying there's an eclipse on April 8th. It'll be about 3 p.m. totality. It will start about an hour before that and go to about an hour after that. And with that, I am going to, if I can change slides, you kind of stole my thunder. I was going to explain that I do magnetic reconnection. This is one of the examples of the simulations that I run. This one is very long, so I picked it because it looks nice. So I just wanted to give like an introduction to myself. I do plasma physics, not necessarily astronomy. So hopefully I will have time to talk about solar flares at the end because it will be relevant, but I promise you all understand it. And then the second part of my introduction is again, sort of just like, here's our map of the eclipse. So we are at the red star and the path of totality is about an hour north of us. These times, if you're squinting at them, are not in Eastern, so don't read off of this. But it will be about 3 p.m., about 3:20-ish p.m., but always better to be early than late. So yeah, I'm going to talk a little bit about what eclipses are, how they happen, what to expect, what you might see the day of, and then some historical observations and discoveries that happen during eclipses, and then some of the science that is going on today or in 2 weeks. So first of all, what is an eclipse? The eclipse is when the moon and our sun align in front of the earth such that the moon's shadow is cast on the earth. They are, I want to say, in the universe, this type of eclipse is pretty rare. It's kind of a coincidence that our sun happens to be about 400 times larger than the moon, and the moon happens to be about 400 times closer to us than the sun does. So it can just perfectly align and block out the surface of the sun. And in later slides, I will show that that's not always the case. There are some eclipses for which that is not the case. But in general, being able to see total eclipses like we can on Earth is pretty rare. Eclipses on Earth are actually also kind of rare. In the sense that we actually do have multiple eclipses per year, as I will also be able to show in this, but the Earth is pretty big and there's lots of water, so a lot of times those eclipses are places we can't see them. So for instance, the next eclipse across the continental US will be in 2045. So I've just said that eclipses can happen whenever the moon and the sun align with the Earth. Why don't we see them every month? Turns out that we do not, because the moon orbits with a 5-degree inclination. So what that means is that if we take the sun and our Earth and we draw a plane between them, so the sun and the Earth are always in that plane, we call it the ecliptic plane, the moon doesn't orbit in that plane. It orbits at an angle. So there's only 2 times when it's in that plane, and we call those nodes, the nodes of its eclipse, the nodes of its orbit. So to get an eclipse, we have to have those nodes line up in between the sun and the Earth, and for the moon to be a new moon. And that happens twice a year. We call this the eclipse season. It's about 30 days long. So we are in one right now, and we will continue to be for, I think it's 2 weeks before and 2 weeks after, but don't quote me on that number specifically. So there are a couple different types of eclipses we can see. As I said before, if the moon's orbit, if the moon is farther away from us in its orbit, we will not get that perfect eclipse. So the moon's apogee, which is the farthest part of its orbit from us, is about 40,000 kilometers farther from Earth than its closest point, which is the perigee. And fun fact, you may have also heard the words aphelion and perihelion, and that refers to the sun's orbit around the Earth. It's the same thing, but it gets called helion instead of G because it's referring to the sun. So these are 3 examples of types of eclipses that we could see. This is a partial eclipse, which is just anything off the path of the eclipse, a total solar eclipse, like what we will get, and then an annular eclipse. And an annular eclipse actually occurred last year across the Midwest in October. Yes, October. So when we are in that eclipse season, The moon is aligned with the Earth the whole time, or sorry, the nodes are aligned with the Earth the whole time. The moon continues around its orbit. But the node in front of the Earth and behind the Earth as well, which means that there is always a lunar eclipse preceding a solar eclipse by about 2 weeks. And I will show this little clip of this is how it happens. The moon goes into the sun's shadow, and then we get the much smaller shadow of the moon to cause our total eclipse. You may or may not have seen the moon about 2 days ago. It was a partial lunar eclipse, so you wouldn't have looked like much. In this video, the moon turned red, but that only happens for a total eclipse, as I will about to explain.
Would you do that again? I'm sorry.
Oh, yes, of course I can.
And slower.
Well, I can't do that, but I can definitely play it again. So this is our lunar eclipse and then the solar eclipse, and it pauses here. I can play it one more time.
Yeah.
Since I cannot, it's a video, so unfortunately I can't change the speed. That would be nice though. Yeah. So we didn't see a red moon. We saw it probably just looked slightly dim if you could see it at all from those clouds. But a total eclipse will look red. You may have heard the term blood moon before. And this happens because the light traveling to the moon is always sunlight. Even when it's a new moon like this, or sorry, an eclipse like this, but the light has to pass through the Earth's atmosphere in this case. And as you can see from here, the sunlight reaching the moon, which will be from the dawn and the dusk sides of the moon, only the red reaches farthest. That's because the lower frequency of light travels farther in our atmosphere. This is the same reason that sunrise and sunset looks orange. The rest of the frequencies are kind of diffused out and cannot travel all the way through the Earth's atmosphere to reach the moon behind it. So I have talked a little bit about what an eclipse actually is, both solar and lunar, and now I will like to talk about how we find them, how we predict them. And these days, NASA is pretty good at that. Orbital mechanics are not that hard. So you get a nice computer and you can pretty much say with certainty when the eclipse is gonna happen. So I'm just gonna give one example of one specific method that can be used to predict lunar eclipses. And this was a particularly interesting one that I thought because this has been around for thousands of years. It was named the Saros cycle in about 1686, but this is a picture of the, I think I can pronounce this right, Antikythera mechanism, which is a cool old clock that the Greeks made, and much, much more than that. We're still trying to figure out everything that's going on with it, but if you believe the internet, this is a recording of the Saros cycle, which is used to predict eclipses. So what is a Saros cycle? It's basically, there are multiple different types of geometries, different arrangements of the sun, moon, and earth in that line that can cause an eclipse. And every 18 years, that specific geometry repeats. So that's one Saros cycle, is that 18 years. And this is an example of the eclipse paths caused by a specific Saros cycle. So you'll see that these are about 18 years apart, and the paths travel on the Earth because 18 years, 11 days, 8 hours, that's the Saros cycle length. But as I'm about to explain, that's not perfect. So we don't have continuous Saros cycles forever. Some come and some go. And that is because a Saros cycle is defined by the alignment of 3 of the moon's orbital periods. So an integer number of 3 different types of lunar months. But it's not exactly perfectly an integer number, so things tend to get out of alignment as the years go past. So what are the 3 orbital periods? It's a synodic month, animalistic month, and draconic month. And so one Saros cycle, those 18 years, corresponds to 223 synodic months, 239, if I can read, animalistic months, and 242 draconic months. The synodic months are what we would regularly think of as lunar months, so just the time between new moons, so when it is aligned with the Earth. is actually the time between, this is also a word that's hard to pronounce, syzygies, which is just a conjunction between the three celestial bodies. It just so happens that our moon is tidally locked, so these are the same things. The animalistic month is the time between two different apogees or two different perigees at the same time. So the time that it takes the moon to go from its farthest point back to its farthest point in its elliptical orbit. And the third one, it's a little bit more complicated. You hopefully can see the moon there in front of the Earth. So the animalistic month is the time between when the moon crosses the elliptical plane. So when it crosses those two nodes, where it is in the same plane as the moon and the Earth, sun and the Earth. So we can use them, and this is very scary, I'll explain it to you, you don't actually have to know what it all means. We can use these to find multiple different series of eclipses. So currently there are 41 different Saros series, which means 41 different types of geometries that can give us an eclipse. This gives us about 2 to 5 eclipses per year as each of these repeat. So this graph is kind of just like a whole bunch of eclipses. So if you could see more clearly the rows going down, these are lists of each eclipse in a Saros series. So as you go down, each eclipse happens 18 years later. Across is a different kind of series called an index series, which I'm not going to spend too much time on, but the difference between that and a Saros series is that it is a alignment of 2 of the months and then half a draconic month. So as you go across, you'll be getting eclipses at every other node, so ascending and then descending. But basically, this is just a big chart of different years in which we have eclipses. And if you wanted to squint at it, you could then tell the next eclipses for, I think, like the next about 100 years are on here. And this is not, of course, the only way we know how to predict eclipses. There's many more methods, including just computing it out, which is probably what NASA does. But I thought that was a good example of the types of things that we have been doing to predict eclipses for thousands of years. And I think I am now going to be moving on to, now that we know when eclipses are, what to expect the day of. So first of all, and I'm sure everybody has been saying this, I'm sure you've heard this before, don't look at the sun without protection. The sun is orders of magnitude brighter than anything else we can that we have on Earth. So any normal fluorescent lighting, you look at it, you'll get a little bit of a burn on your retina. You look at the sun, that's 100 times worse burn at least. And especially during the eclipse is dangerous because the sun, as it starts to block out light, our eyes go, oh, there's less light, I don't have to be as worried. So they open wide to see more, but there is not 100% of the UV light being blocked. So you can very easily get a sunburn on your retina without even realizing it. So different ways that you may or may not have heard of is use those glasses. There's other types of solar filters that you can use that basically just block out, 90% of the sun's light. You can also use solar telescopes. I believe Dartmouth will have solar telescopes with H-alpha filters, both here and at our event in St. Johnsbury. Or you can use pinhole projectors, in which case you are looking at a projection of the sun and not the sun, so you're safe. The exception to this is during the totality. So for about 2 minutes of totality, you can look at the sun with your visual eyes, and that's where you see the corona. But just like be aware, it's only 2 minutes. You gotta be pretty careful about that. But yeah, so when you are looking at the sun during totality, what can we expect to see? There's 3 different things that I want to highlight here with this picture of a total solar eclipse. The first is that really bright diamond ring effect that you see here at the top. This is also called Bailey's beads, and this happens when sunlight comes through right at the beginning and the end of totality through a valley on the lunar surface. So we may or may not see it this time. The other 2 things that you can see is this red ring. This ring is not the corona, this is the chromosphere, and this red comes from hydrogen in the chromosphere giving off red light. And the third is, this is labeled as a solar prominence. This is just a structure in the solar corona. And my next slide I think will give you a little bit more of an idea of what these terms that I've just said to you mean. So there's a lot of stuff going on inside the sun. There's the core. There's fusion going on in there. I will have a slide for that in a minute. But what we care about right now is the atmosphere of the sun. So the photosphere is the bright part of the sun. That's what we call the surface. That's the visible end to the sun. And that's what's being blocked out by the moon. The chromosphere is a layer right above that. That's characterized by that red color. And then above that is the actual atmosphere of the sun, the corona. And there's lots of behaviors going on in the corona that are look very cool, and I can boil them down basically to there's magnetic fields there. The magnetic fields are very complicated, and there's plasma following the magnetic field lines. So we have a whole bunch of different types of behaviors, and these are just some of them. We have open field lines, where these field lines, magnetic field lines, are connecting away from the sun out into like the interstellar medium. We have closed field lines that cause the coronal loops, where these are closed back into the Earth, and both of these have plasma traveling along them. We have helmet streamers, which are a specific type of open field lines that usually denote sunspots, and then these prominences, which are some cooler plasma. And you can see here that red color again. That's because that's plasma from the chromosphere traveling up. And I will talk a little bit more about the corona and when I talk about some of the current research going on. But so I've talked about the outside of the sun, and I've given you some explanation of what you might see. Now I would like to get into the physics. In I don't know what's going on there. Helium physics is the study of our sun, and hopefully I can give you a good enough explanation, a quick explanation to be able to explain the types of physics that are being studied currently with this eclipse. So I will start with that the sun is powered by fusion. All stars are powered by fusion. This is sort of a diagram of how that happens. Basically, fusion is the combination of two light elements into a heavier element, and they give off a bunch of energy. In the sun turns hydrogen into helium through this, which is called the proton-proton chain fusion, which, fun fact, is a different type of fusion than what we are trying to achieve on Earth. So in terrestrial reactors, we cannot achieve the high pressures in the sun because the sun is gravitationally confined. All that plasma is being pulled together by its enormous weight. We don't have that on Earth, obviously. So we have to compensate by creating incredibly hot plasma, and that plasma fuses hydrogen into helium in a different way. And back to the sun from that tangent, which you'll have to excuse me for because fusion is my field of study. The sun is made up of mostly hydrogen, but it has, at this point, fused about 8% of that into helium. And then there are some other trace heavier elements in there as well that it has created. So the sun, as I just said, I know that I just said that on Earth we create hot things, but the sun is still pretty hot, even if it's not as hot as a fusion reactor. So all of that hydrogen and helium in the sun is ionized. And what that means is that the electrons have been stripped from the atoms. So we have positively charged nuclei and negatively charged electrons, and they are all moving around together, and that generates magnetic fields. So this picture down here shows one example of what the sun's magnetic fields might look like at a given time. It's pretty complicated. Even plasma physicists think it's pretty complicated. We're not exactly sure everything that's going on. But those magnetic fields and the plasma that follows them are what is responsible for all of the solar activity. So sunspots, flares, coronal mass ejections, and that activity follows in about 11-year cycle. In about 2025, I think we'll be reaching the maximum of that cycle, so the sun will be at its most active, and then it will start to diminish again. So the important thing about our sun is that it gives off light. It gives off those photons as heat and energy and light. But it also gives off both plasma and magnetic fields. And we call this the solar wind, and it streams out into our solar system, and more importantly, it has to pass by the Earth, and so it interacts with our magnetic field and our atmosphere to cause space weather. So space weather and space physics, which is a study of that, is just studying how that solar wind interacts with us and what types of things it can do. So I will show you this video if I can get it to play. Perhaps. Oh, there we go. Great. Okay. So this is just one example of the types of behavior that we get from the sun interacting with our magnetosphere. This is solar wind, which is given off by the sun, has a magnetic field, interacts with the Earth's magnetic field, and magnetic reconnection happens. This is something called the Dungy cycle. So you can see these lines are magnetic fields. When they interact with the sun's magnetic field, they break and are peeled back to the Earth. And then they will reconnect in that tail behind the Earth and send a whole bunch of energetic particles down to our poles, and that's what creates auroras. There are a whole bunch of other interactions that the solar wind can have with our atmosphere, including, if you heard of the Carrington event, it was a very large coronal mass ejection that disrupted power lines. I think at that point in time it was like telegraph lines, but certainly an event of that size could definitely cause some damage to our current infrastructure. So knowing how that works and how to predict it is very important. The other thing that I will mention now, because it will come again, is the sun ionizes our atmosphere. So it gives our atmosphere enough energy to break those electrons off of the atoms and form the ionosphere. And that ionosphere can affect radio communications both on Earth and to spacecraft. And I will let the rest of this video play because I think it's pretty cool. I will go to the next slide. So this is sort of just background on the physics of the sun. And now I would like to move into some of the actual discoveries that have happened during eclipses. So basically these historic discoveries fall into the camp of the sun is really bright. And when it's blocked, there's other things we can see. It's also something that is very observable, and people have been making scientific or historic records of it for many, many, many years. And so some of the things that we have seen during eclipses include measurements of the moon and the Earth's orbits, and the orbits of other planets. We looked for and then did not find the planet Vulcan, which people thought could be an explanation for why Venus's orbit was weird. Turns out that there's no planet Vulcan, it's just general relativity. We have ancient records of when solar eclipses happened and where, and these records helped us to show that the Earth's rotation speed is slowing. So this purple graph here shows a line where eclipses have happened and the line where the eclipses should have happened if the rotation of the Earth is the same as it was today. And obviously these two don't match up. So we have proof that the Earth has changed its rotation speed. And that, I believe, tablet is a record of one such eclipse that helps us prove this. And then lastly, of course, we wouldn't have known the corona was there if the sunlight hadn't been blocked off so we could see it. So first observations of the corona and then scientific observations of that sense of the temperature and its composition are still mostly done during eclipses. And then two more experiments that I'm going to single out because I thought they were pretty cool. The first is the discovery of helium. So helium was first observed by people looking at the corona. During the 1868 solar eclipse, astronomers saw a wavelength of light that did not correspond to any known element. So let me first explain spectroscopy, which is basically how all of astronomy is done. Every element can absorb and emit only specific frequencies of light, and these frequencies of light correspond to the energy levels of the electrons. So electrons are quantized, they can only accept certain amounts of energy, and which means that atoms can only absorb and emit energy that corresponds to those levels that the electrons can be at. And I promise I won't talk any more about quantum physics today. So this is a picture of a helium lamp, works pretty much just like a regular neon sign, it's just a different noble gas. And then here is an example of a spectrum that astronomers can use to tell what's on the sun. So this is the broad spectrum of the sun. The sun emits all frequencies of light. But if there's hydrogen in the way, that hydrogen will absorb specific frequencies of light, about 4 lines. I think there's a 5th one here that you may or may not be able to see. So if we see this spectrum, we know there's hydrogen. And then the rest of these lines correspond to other elements that are on the sun. And that's how we know what the sun is made out of. So the astronomer who discovered this, there's actually 2 of them. Pierre Janssen first observed it during an eclipse. And this motivated him to go back and figure out how to look at the sun without there being an eclipse so he could tell more. He saw this yellow line here, and previously it had thought to be that this yellow line was from sodium, but it did not match up with the actual frequency that we knew sodium to be at, so it was a new element. Independently, an astronomer named Joseph Lockyer also observed this line, and he also developed a way to look at the sun without an eclipse. So these 2 are both separately credited as discovering helium because there was no telephones. They didn't know that it had already been seen in an eclipse. But we didn't actually see helium on Earth or get to know any of its chemical properties until much later. So only in 1882 was helium observed on Earth, and was observed by an astronomer named Luigi Pellimeri, and he actually saw it in a eruption of Mount Vesuvius. I don't know why there was helium in Vesuvius, but I think it's pretty cool. And then in 1889, it was first isolated and studied on Earth, and that was when they proved this spectrum belonged to helium, and helium was, it's a noble gas, it's atomic number 2, etc. And that was done by the chemists Kirchhoff and Bunsen, and this is a picture of their spectroscope in which they were proving that the helium that they had isolated did in fact give off this spectrum. And then the second discovery that I'm going to look at, this one's not actually a discovery, but an experiment which confirmed general relativity. So in 1915, about 4 years before that, Einstein had proposed general relativity, and people were trying to figure out how to prove it because it was pretty out there. General relativity proposes that gravity is caused not by a regular force like Newton thought, but by the bending of space-time around massive objects and also energetic objects. So that would mean that as light passes by the sun, it's bent by our gravitational field. Newtonian gravity also calls for this, which is called gravitational lensing, but the angle that it predicts is much different. So by measuring the angle, we can tell that it is in fact the general relativity causing this. So this angle, and this is the only math in the presentation, tells us what angle we expect a sun's light or a distant star's light to be bent as it passes through the sun. And basically what it tells us is that it'll be very small. So for us to see that angle big enough to measure, we would need the light of the star to pass incredibly close to the sun, which normally we would not be able to see it. So this experiment called for measuring the apparent position of a star near the sun, as near to the sun as possible, and then coming back and observing the position of that star when there is not a sun in the sky, and comparing those 2 positions to tell us the angle at which the light has been deflected. And this was attempted multiple times in the intervening 4 years before the Eddington experiment, and nobody succeeded until they did. I think there was like at least 2 or 3 other groups who tried to do this, and one of them was a group of Americans who just messed up the study. They just didn't do it right. And I think, don't quote me on this, I think one of them was a group of German scientists who were in the wrong place at the wrong time and got captured when a war started. So I hope they're all right, but good on Eddington and his friends for actually achieving this. So the 3 astronomers who actually observed this were Arthur Eddington, who went to Australia, I believe, Frank Watson Dyson, who did not see an eclipse, just stayed in Britain, and Andrew Crommelin, who saw the eclipse in Brazil. and this is a picture of his solar telescope in Brazil. And this is according to some museum in Europe, the best replication we have of the photo plate that Cromlin took in Brazil. So that is some previous discoveries that we have from eclipses, and now I'm going to move on a little bit. Hopefully I'm not too far behind, but maybe I am. So I'll talk quickly. So we have the main two different types of studies going on is studying the Earth's atmosphere and the Sun's atmosphere. There's plenty of other studies going on, but I just want to focus on these because these are the main ones. So studying the Earth's atmosphere, we have a couple different projects. The Nationwide Eclipse Ballooning Project, which is just many different people sending up weather balloons with little sensors on them to see how the eclipse is going to affect our atmosphere. The ham radio citizen science, which if you have a ham radio and want to do citizen science, I would definitely recommend looking that up. It's basically just looking at how communications are affected by the eclipse. Superdaughter observations of how the radiation changes are going to affect our upper atmosphere. This is a picture of one of the superdaughter radars. I think this is probably in the North Pole. Usually superdaughers look at auroras, so perfect for how radiation interacts with our atmosphere. And then the one that I'm going to talk a little bit more about is the sounding rocket campaign, which will be looking at how the eclipse affects our ionosphere. And then on the sun's surface, looking at the corona with some high altitude planes and looking at the sunspots using radio telescopes. And this is some observations from, I believe, the 2017 eclipse of those sunspots. So first, this is called the atmospheric perturbations around the eclipse path. Sorry, my title is blocked on my screen. And if you believe them, this is named after an Egyptian god who fought Ra, the sun god. That seems reasonable. NASA has lots of fun coming up with their acronyms. But anyway, 3 rockets will be launched from the NASA flight facility in Wallops, Virginia, before the eclipse, after the eclipse, and then during the eclipse. These are the same 3 rockets that were launched during the annular eclipse last year, and they will be taking the same measurements. This project is led by Embry-Riddle, but sensors on those rockets are being built by some of our physicists here. So Professor Christina Lynch and grad student Magda Moses are the ones who built some of those sensors. And they also are going to have a talk on April 2nd, I believe, at the Dartmouth Library. So if you're interested more in the instrumentation and exactly what they're doing, I would definitely recommend that. But these instruments, they will measure the density of neutral particles, the density of ions, and then the electric and magnetic fields. So one of the main reasons that we are interested in looking at the eclipse and how that affects the ionosphere is that the ionosphere, its conditions are dependent on the sun ionizing it. So as the sun rises and sets, the ionosphere changes. During the nighttime, there's much less ionization. It's much quieter and less energetic. And the eclipse will cause this change from ionized to low energy back to ionized in a matter of minutes and hours instead of one day. This is an animation of the 2017 eclipse and how it affected ionization. And as you can see, there's these waves that go away from the path of the sun. They're a little bit clear right here. So the main thing that they're hoping to see, I believe, is these perturbations away from the path of the eclipse. And understanding this will help us understand just the ionosphere in general, and having a good model of that is pretty important because it can affect our communication signals. The ionosphere can reflect or absorb radio signals, and it can distort signals traveling through it to space. And now I'm going to, I'm doing okay on time. Talk about this is my last subject, is the corona, and hopefully I'll have time to talk a little bit about solar flares. So NASA is studying the corona using a high altitude aircraft that will be carrying Sensors from two main projects. The University of Hawaii will be studying with spectrometers the temperature, composition of the corona, and the origin of the solar wind. And the Southwest Research Institute of Colorado will be using an experimental IR and visual light camera to study the structure of the corona and coronal mass ejections. And this is a picture that they took with that camera at our last eclipse. So what's so interesting about the corona? One of the main things that we are studying with the corona and its behavior is why it's so hot. So the core of the sun is pretty hot. That makes sense. That's where the fusion is happening. That's where the energy is released. As it travels up to the photosphere, it gets cooler. And then in the atmosphere of the sun, the plasma up there gets way hotter. We know this because of observations done in 1869 during an eclipse of looking at, again, the spectroscopy of the corona. They saw this green line that for a while they didn't know what it was. They thought maybe it was a new element. They called it coronium. But in 1938, they figured out that it is in fact iron that had been ionized 13 times, which means that the corona is energetic enough, hot enough to strip 13 electrons off of iron. For this to be possible, the corona would have to be 200 times hotter than the photosphere. And figuring out why that is still an ongoing investigation. Although I would like to think we're a lot closer than we were in 1939. Two main theories we have are basically different ways of transferring energy from the photosphere into that plasma is that it's moved by electromagnetic plasma waves called alpha waves that travel along the magnetic field and magnetic reconnection. So now I get to tell you guys a little bit about magnetic reconnection. So this is found basically everywhere there's plasma. All you need to have is magnetic field lines that are oppositely oriented. So this is our favorite GIF. This is an every reconnection presentation. Thank you to the person on Wikipedia who made it. These red and blue lines are the field lines, and you can see that they are anti-parallel to each other. And when they touch in the middle there, they reconnect and fling themselves and all their energy out to the sides. So magnetic field lines can store a lot of energy, kind of like a stretched rubber band. They have tension in them. And you can see here that when they break and reconnect, these are very highly curved. And so they have a lot of tension and want to go slingshotting off. And so that's what they do. And in the process of that, they transfer a lot of energy into the plasma. They heat it, they accelerate it, they cause X-rays, which is how we see these flares. And so we're thinking it transfers a lot of energy. That's probably at least one of the pieces of the puzzle to explain why the corona is so hot. This is because I'm talking about magnetic reconnection, I had to put another one of my own simulations in there. This is a picture of, an animation of the magnetic field. So those lines are the magnetic field lines along which plasma travels, and the color is the strength of the magnetic field. So this is just showing process of reconnection and then some other behavior that happens in my simulation because of boundary conditions and things. So heating can be done, we think, not by the main large solar flares, but by reconnection events that are much smaller than that, which we call microflares. So each microflare releases about 10 to the 19 joules of energy, which is 10,000 megatons of energy, which is lots of nuclear bombs stacked on top of each other. So when I say small, I don't mean like small. These are small compared to regular large flares and coronal mass ejections. So they're about 1 million times smaller than a regular flare, but they happen a lot more often and closer to the solar surface. So we think that these flares, and this is a visualization, not an actual picture, could be what is throwing that hot plasma up and heating it. And the other thing that magnetic reconnection can do for us is that it can generate those electromagnetic waves that then move more energy up into the corona. So these are they feed back on each other, and there's other turbulent processes that can be involved in moving that energy, but we think that these two are our main culprits for moving all that energy, taking basically the magnetic energy at the surface of the sun and putting it into thermal energy up in the atmosphere. And that is all of the science that I have to talk about for today, but I wanted to highlight a few other events going on. We have, like I said, we have a talk at Baker So one of those talks is going to be by Christina and Magda on their sounding rockets. One of those is by John Thorstenson, and it will be again about just a more general eclipse stuff. One of our other professors is giving a talk at Peery, and then I believe that's our only information events, but the Montshire is going to have events the day before and the day of the eclipse all day. Dartmouth is going to be in St. Johnsbury at the Fairbanks Museum. I believe we will also have the telescope set up here on the green to look at the partial eclipse. And I'm sure there's other, like the University of Vermont is going to have stuff going on as well. So my last two slides are, and these are pulled from a NASA information. These are like citizen science opportunities. So I just added in here in case anybody wanted that information, wanted to participate in that. There is this one, which is, I believe, just taking observations during the eclipse. There is the Jet Hunter, where it's looking for specifically events in the corona. And then I do not have information because I already mentioned it, but the ham radio contest. So I would suggest definitely looking more into these if you are interested in participating in anything like this. And thank you, and I am happy to take as many questions as you have. All right, that was perfectly on time. Great. Yeah.
Do you need to have a filter on your camera if you're gonna photograph the solar eclipse?
Yes, but not because it'll hurt your eyes looking through the camera, but because it'll probably hurt your camera a little bit. Yeah. But like it won't kill you. But like I would still suggest yes. Yeah.
So specific to Hanover in the Upper Valley, because we're not in the path of totality, it's always going to be a partial eclipse.
Yes.
And we can never look at it directly then, right?
Yes.
Okay.
Yeah.
You were talking about how they were able to measure that the orbit of the planets have changed over time
Mm-hmm.
through these eclipses. So is it just partial seconds changes? What kind of a change are we talking about?
That is a good question. I believe it's probably more of a matter of minutes.
Minutes.
Because we know it's a big enough change that we can say, if we have a record of some civilization saying we had a solar eclipse on this day, and our astronomers can go, oh, well, if the Earth had rotated as fast as we thought, your path of totality would be somewhere completely different. So it would be that the difference enough to make up for that of the path of totality having totally shifted.
So if that's the case and it's minutes, is that part of leap year? Trying to.
That's a good question. No, so I think leap year is just that our solar year, our orbit isn't exactly 365 days. It's just slightly longer than that. Okay. I think this would be more an effect of the moon. So the moon is pulling on us and we're pulling on the moon. That's sort of slowing how we rotate.
So how do we change our clocks to?
I think we will be long, long dead before it makes an impact on our lives. Yeah.
I was just curious how the experience would be different being at like the edge of the totality band versus in the middle of the band. Is it just that you see totality longer, or is there any?
Yeah, that's pretty much it. Is like once you're in that band of totality, you will get the like it'll look the same while it's totally eclipsed. It just won't last as long if you're at the edge. Yeah.
Are there any places you recommend to visit see the eclipse?
Yeah, so like I said, Dartmouth is going to be at St. Johnsbury, which I believe is about an hour and a half drive from here. Burlington will also be in the path of totality, I believe. But I'm sure other universities are going to have H-alpha filters, but I know we will. And looking at the sun through an H-alpha filter is pretty cool because you can actually see the solar flares. So that's what I would recommend is St. Johnsbury.
So we have a question from Zoom.
Yeah.
Heidi is wondering, how often do the conditions of the ionosphere disrupt Earth's communications?
Probably every day. So the length that radio waves can travel changes with the day and night cycle. So yeah, constantly, basically. Yeah.
The day of the eclipse, will our communications with cell phones and Wi-Fi be interrupted?
So probably not with Wi-Fi. This would be more like specific radio frequencies that are going to be like emitted based on how our ionosphere works. So I don't think we should see any like, we don't expect to see any kind of like large scale disruption. But like again, if you had a ham radio, I'm sure you would see differences in where you could get a signal and couldn't. Yeah.
What would happen if a satellite passed through between Earth and the moon while this is going on? Nothing?
Not much, I don't think. Because it'll still be in between us and the moon, so we'll see it like normal. I guess it'll have some of its light blocked out. Hopefully it doesn't need the solar panels to be charged at that point, but yeah.
And are the airplanes that are going to be involved during the eclipse, are they going to fly through the path of totality?
Yes, so they're actually going to be chasing, those high altitude spacecraft that NASA is launching are going to be chasing totality. And by flying along the path of the eclipse, they gain, I think it was about like 2 or 3 minutes of totality, which brings them up to about 6, whereas us on the ground don't get that many. So yeah, they're definitely going to be chasing the eclipse.
How would act like typical regular planes? Like would their signals be disrupted, or are they trying to stay out of the path of totality, or it doesn't impact flights at all?
I would think it wouldn't have too big of an impact. So the picture that I showed of the ionosphere perturbations, that would probably be like the biggest place where disruptions come from. I know there are actually like many planes that are going to be doing the same kind of thing of like chasing totality. You could probably spend thousands and thousands of dollars in getting a VIP seat on one to see the eclipse from the air. So they're not worried about like planes crashing or anything like that.
I'm sure the glasses the library is going to give us are perfectly safe, but could you reassure me a little?
Yeah.
How they function?
So they just basically block out just like so much light. So if you were to hold one up, you just wouldn't be able to see literally anything else besides the sun. And the sun is going to look like just like a little red ball. But basically, I mean, like we've all kind of squinted at the sun once or twice. If you squint at the sun for like 1 second, it's going to be the same as it is every day. You're going to look away. Basically, it's just there's no other times when people are trying to look at the sun. So that's why we are spending so much effort in telling people not to do that, because why else would you if it wasn't an eclipse? But yeah, those glasses block out like I'd probably like 95% of the light. And if you look at them, you just see a little bit of them. Yeah.
Just on that note, there are retailers who say that they have these solar glasses available. I went to CVS and there is a brand done by Foster Grant that says solar something.
Mm-hmm.
It's not for the eclipse.
Okay.
The cheap little paper ones that we're getting are the only way to go.
Yeah.
Don't be deceived by manufacturers' advertising.
Yes, I think they are required to put on like ISO compliance, so you should be able to see on your glasses, hopefully.
Yeah.
I'm not 100% positive since I'm not holding one, but they should say some kind of regulation.
At least they gave me my money back, so I was okay.
Yeah, great, yeah, good to hear. Yes.
So if I understand you correctly, you're not saying that looking at the sun at the eclipse is inherently like more dangerous than looking at the sun anytime. It's just that we're more likely to look directly at the sun because of the eclipse.
Yeah, pretty much. So there is that, like, when the sun is almost at totality, most of the light is blocked. So if you were to squint at it like just like minutes before totality, your eyes wouldn't react as well because it's not as bright as normal. But the UV light isn't completely blocked, so that could be a little bit more dangerous. So, but just like right around totality, the fact that It doesn't look as bright as usual, so we don't get that flinch response, but it can still be powerful and dangerous. But yeah, mostly it's the danger is that normally people don't look at the sun.
Have not a question, but two comments.
Yeah.
We are very fortunate to live in the Upper Valley where we have brilliant young scientists and a library that brings us all together. So thank you for you, this is complicated.
Yeah.
We were impressed. Thank you very much.
Yeah, thank you for trying.
It's a great note to end on. Thank you so much, Sarah.
Yeah, thank you.